We will now see a little bit of recap on differential equations that need integrating factors to integrate. Now, one very standard form of writing differential equation is the m dx plus n dy is equal to 0, where m and n are each functions of x and y respectively. In other words, m is m of xy and n is n of xy. Now, it may be in this form either an exact equation or it may be an inexact equation. We say that m dx plus n dy is equal to 0 is exact when this left hand side is a perfect differential, which is equal to du, where u itself is a function of x and y. So, when that happens, we can write the equation as du is equal to 0, because m dx plus n dy is equal to 0, so du is equal to 0, and when you have du is equal to 0, the integral of du has to be a constant. In other words, u is equal to c is the solution. So of whichever function u, this m dx plus n dy is the differential, that equated to c is the solution for the exact differential function. But most often than not, because life is not simple, most of the equations that we have given in this form are inexact. It is all right to revisit the condition for exactness, and that is, if equation has to be exact, then del m del y is equal to del n del x. That means the partial derivative of the m function with respect to y must be equal to the partial derivative of the n function with respect to x. But in the case of inexact differential equations, that is not so. So we have to invite an additional function that multiplies the entire equation through and converts it to an exact equation, and we will visit some of those integrating factors one by one. Here we can re-mention that when we are integrating this m dx plus n dy and writing it is equal to c, the integration is with respect to x for the mxy terms and with respect to y for the nxy terms, and taking care to omit any term that has already appeared in this first integration. So when we integrate this second one, we have to take care not to repeat any terms that appear here but which have already appeared in this integration. That is very important. That means double count is not allowed. M and N are homogeneous functions. Of the same degree in x and y. This is an important concept. I mean, there are many functions which are homogeneous. We will see the criterion for m and n both being homogeneous, and they have to be of the same degree. If that is so for a particular combination of m and n, and we find that del m del y is not equal to del n del x, then an IF, not the IF, because integrating factors can be many for the same equation. It's not unique. Then an IF is 1 over mx plus ny. This has been given without proof. We'll just see one equation. So this integrating factor will render this particular equation into an exact equation. Now we will have to take up separately right now what exactly is the meaning of homogeneous function in x and y. So we'll do that before we tackle a particular problem with an example using this rule. Any function f x y or g x y or whatever you call it is homogeneous in x and y x and y and is homogeneous in x and y and of degree n if and only if f lambda x lambda y can be passed as lambda to the power n f x y. In other words, if in the function f x y each x term is replaced by lambda x and y term is replaced by lambda y, and the resultant is lambda to the power of some n into fxy, then that particular function is termed a homogeneous function of degree n. We'll take a few, one or two small examples to see whether the functions are homogeneous or not. This lambda, must be remembered, is a parameter and is independent of x and y. That's very important. Call it lambda, call it t. It must be independent of x and y. Consider fxy as x cubed plus y cubed over x squared minus y squared. Then f of lambda x lambda y is lambda cube x cube plus y cube and lambda square into x square minus y square. In other words, this is equal to lambda to the power of 1 fxy. Fxy is this one. This part is fxy. So we say that the given function is a homogeneous function of degree 1. Now there is, sometimes many students feel that if the degree of all the terms are same, then the function can be termed as homogeneous. So Let's take an example of such a situation and show that the function is not homogeneous. We go over the degree same concept. So let us take one example in which the concept of terms of the same degree leads to homogeneous function does not really apply. So we take a simple function. Supposing if xy is simply tan inverse x cubed plus y cubed over x square minus y square. We just saw a little while ago that this function without the tan inverse part, this is homogeneous function of degree 1 because we proved that function lambda x, lambda y, which this is the fxy, gives lambda to the power of 1 fxy. Now, here, if lambda x, lambda y is tan inverse lambda to the power of 1 x cube plus y cube over x square minus y square. Now, whoever said that tan inverse of this is the same as tan inverse of lambda to the power of 1 into this, that's only true when lambda is a parameter chosen as 1, not otherwise. But lambda is a parameter independent of x and y, not necessarily equal to 1. So, the degree same concept does not hold for homogeneous functions of x and y. Now, we will take an example of integrating factor. So, one form, of course, the first form that we are discussing is form M where M and N are homogeneous functions of x and y. Then the integrating factor is 1 over mx plus ny. Assuming that mx plus ny is not identically equal to 0. We take an example and then the point will be driven home better. So, we will now go to an example in which this criterion is fulfilled and see how 1 over mx plus ny as an integrating factor multiplying this original equation leads to a solution very quickly. So, we have chosen this particular example to solve by using the integrating factor we just now discussed. Here, as we said, m and n are both homogeneous functions of the third degree, and we will see that del m del y is not equal to del n del x. So, we do these operations separately. Del m del y is actually equal to x square minus 4xy, that is differentiating this with respect to y, keeping x constant, 4xy, and del n del x is equal to differentiate with respect to x, keeping y constant, so 6xy minus 3x square. Obviously, they are not equal to each other. So, here del m del y is not equal to del n del x, and hence the equation is not an exact equation. So, we will have to invoke an integrating factor which we have said is 1 over mx plus ny. So, we will just now proceed to evaluate what is the value of mx plus ny. Clearly, mx is equal to this multiplied by x, so x cubed y minus 2x square y square plus, that is mx, plus nothing, and ny is this multiplied by y, so 3x square y square minus x cubed y. So that is there. M into x is x cubed y minus 2x square y square, and ny is 3x square y square minus x cubed y. When we add them up to get mx plus ny, these two terms will annihilate each other, and 3x square minus 2x square y square is x square y square. So evidently mx plus ny is x square y square, implying that the integrating factor here is 1 over x square y square, according to the rule that we just discussed. So the integrating factor is 1 over x square plus y square. So what we will do is we will multiply the given equation, which was inexact, by the integrating factor 1 over x square plus y, x square y square, to convert it to an exact equation. We will capture that here. IF is equal to 1 over x square y square. So multiplying through by 1 over x square y square leads us to x square y minus 2xy square over x square y square dx plus 3x square y minus x cubed over x square y square dy is equal to 0. If we rub out what we have on top, we will get the simplified result right on top, and then we will perform the integration. Now, this from here we get x square y divided by x square y square is 1 by y. 1 by y minus 2xy square divided by x square minus 2 by x. Plus this divided by x square y square is 3 over y. Minus x over y square. So we have this as an equation of the form fresh m dx plus n dy is equal to 0, where we now know, and it can easily be verified also, that this particular function, when which is a new m, we can call it m dashed, and this particular function can be given a name n dashed. One can easily verify that del m dashed is equal to so we just integrate this as if it is an exact equation, which it is, and follow the rule of integrating an exact equation. In other words, we will integrate this part with respect to x, keeping the y term as constant, treating the y term as constant, and this with respect to y, treating the x term as constant and taking care not to repeat any term in the second integral which is already emerged in the first integration. So, doing that integration, we write integral if I integrate this with respect to x, I get x over y minus, if I integrate this, 2 log base ex plus 3 log base ey. With respect to y, this gives me plus x over y as c. This is the required solution. In other words, we can combine these two and write 2x over y. No, that's not right. If I have x over y coming here and being repeated here, I must ignore this term and cancel it, not combine it with the first. That is as per rule, because we said we integrate the second one with respect to y, taking care to omit any term in the second integration which has already appeared in the first integration. So, that has to be omitted. So, following that rule, we ignore this term, and the solution therefore is x over y minus 2 log x plus 3 log y base e is constant.